Welcome back. In this lecture, we are going to discuss on power MOSFETs. MOSFETs are basically the metal oxide semiconductor field effect transistor, and they are used for power applications. Let us see the outline. We will be discussing the power MOSFET, the types and symbols, what is the operating principle, the static characteristic and the dynamic characteristic, what are the parasitic elements, the gate drive requirements, the power losses in the MOSFET and the thermal management, paralleling of the MOSFETs. We will compare the MOSFET with BJT, see the selection guidelines and applications, what are the protection and practical consideration, recent development and the conclusion. So let us start with the power MOSFET. Power MOSFET is basically the high power version of the conventional MOSFET that we have already discussed in the electronics. So high power is the keyword when we take the power MOSFET. They are designed to handle high voltage up to several kilovolt and current up to 100 of amperes. So the voltage is very high in the range of kilovolt and the current is also very high in the range of 100 of amperes. They have the combined advantage of MOSFET, which are electronic MOSFET, with power handling capability. They are basically the voltage control device, unlike the BJTs, which are current control device. So when we talk about the BJT, that is the bipolar junction transistor, they are basically the current control device, whereas the MOSFET are basically the voltage control device. Dominant device in basically the low to medium voltage power electronics. So when we have the application of power electronics in the range of low to medium voltage, then this equipment is one of the most dominant equipment in power electronics. Some of the key applications of MOSFETs are used in switch mode power supplies, the motor drives and the inverters, in the DC to DC converter, automotive electronics and LED drivers. MOSFETs are basically the three-terminal device. The three terminals are basically the gate, the drain and the source. Gate control the terminal which is analogous to base of the BJT. The drain is basically the output terminal which is analogous to collector of the BJT. The source here is the reference terminal which is analogous to emitter of the BJT. So this is the figure which shows the structural schematic of N-channel MOSFET. There are two types of MOSFET we will be discussing. One is N-channel and another one is the P-channel. So here we can see the terminal. So this is the terminal number 1, which is the gate. The terminal number 2 is basically the drain and the terminal number 3 is basically the source. So MOSFET is basically the three-terminal device. So it is a N-channel MOSFET. So it is represented in the form of NPN. The key characteristic of this MOSFET is they control the current flow from drain to source by gate source voltage. So we will be connecting one voltage source between the gate to source, which will be controlling the current which is flowing from drain to source. So from drain to source, the current which is flowing will be controlled by the voltage source between the gate to source. The input impedance is very high in the range of mega ohms and they give unidirectional current flow when the MOSFET is on. They block the voltage in only one direction when off. So MOSFET when off, they will be blocking the voltage in only one direction. When we talk about the power MOSFET structure, the basic structure have N plus source region. They have P-type substrate, which is the body, and N minus drain region, which is lightly doped. It is having the metal gate electrode and there is insulating oxide layer which is made up of silicon oxide. The operating principle which is having the gate voltage which will be creating the electric field and the field will attract or repel the charge and as a result there will be forming the conducting channel which will control the current flow. So this is the very brief operating principle which is because of the source which is connected between the gate to source and the drain to source, there is a current which is flowing. So here you have the cross-sectional structure. So you can see this is the gate, drain, and this is the source, 3 terminals you have. And here you have the N-type, P-type and N-type material, and you have all the capacitances which are forming because of the insulating material between the electrodes. When we talk about the types of power MOSFET, they are basically based on first category, that is the channel type. So in the channel type, you have N-channel MOSFET and P-channel MOSFET. When we talk about the N-channel MOSFET, they are the more common. Electrons are the majority carriers in there because of the term N stands for electrons. P, which stands for holes, are the majority carriers here, and they have the slower switching. So generally we use N-channel MOSFET. When we divide the power MOSFET based on the operation mode, you have the enhancement mode and depletion mode. Enhancement mode normally represent the off. It requires a positive gate to source voltage to turn on. In the depletion mode, it is normally in the on state, that is the MOSFET is in the on state, and it will require the negative gate to source voltage to turn it off. Again, based on construction, the MOSFETs are divided into 3 important categories. One is known as the VDMOS, which is vertical double diffused MOS, UMOS, which is U-groove MOS structure, trench MOSFET, which is vertical trench gate structure. Our focus of discussion will be the fundamental principle and the operation. We are not going to discuss much more on the construction side. Power MOSFET are typically basically N-channel enhancement mode device. So when we talk about the power MOSFET, generally we will be talking about the N-channel and in the enhancement mode. Let us see the symbols and how the body diode plays an important role. In the symbol, we have N-channel, which is the arrow which is pointing inward towards the channel. So here you can see the 2 important MOSFET. One is the N-channel MOSFET and another is the P-channel MOSFET. So these are the 3 terminals, gate, source and drain. And this arrowhead is the one which represent the difference between the N-channel and the P-channel. So when we talk about the N-channel, it will be towards the channel. So you can see the arrow point head, it is towards the channel. Whereas when we talk about the P-channel, the arrowhead will be away from the channel. So here it is away from the channel. There is a broken line here which represent the enhancement mode, which is normally the off state. Solid line, there is another one solid line here, which is the depletion mode, and it is rarely used. The body diode, which is basically the intrinsic diode, this is the parasitic diode which is between the drain and the source. They provide the reverse current path and they are useful in the bridge circuit, which will eliminate the need for external freewheeling diode. We have discussed about the freewheeling diode in our earlier lectures, where the presence of inductor and why the freewheeling diode is required to pass the current. You can see those lectures. So this is the intrinsic diode what you have. Now the MOSFET operation during the turn-on process, we will be taking the example of N-channel enhancement mode MOSFET, which is more common. So here the gate to source voltage, if it is less than the threshold voltage, then the device will be off state. And in the off state, there will be no conducting channel existing and only the leakage current will be flowing. So drain current will be approximately equal to 0. When the gate to source voltage is equal to the threshold condition or the threshold voltage, then we require typically the threshold voltage around 2 to 4 volt for the power MOSFET. And here you have the weak inversion, which is now the channel will be begin to conduct. So VGS, gate to source voltage, when it is more than the threshold voltage, then you will be having the channel formation. Electric field will attract the electron to the surface. It will form the N-type conducting channel, and as a result, the current will start flowing from the drain to source. And as you increase the VGS, that is the gate to source voltage, the channel will become more wider and you will be getting more current. So gate to source voltage generally in the range of 10 to 15 volt you will be having the full enhancement mode of operation, and this is the maximum channel conductivity, and you will be having the minimum on resistance which will be achieved. In the operating region of this power MOSFET, we have three important regions. One is the cutoff region, second is the ohmic or the linear region, third is the saturation or the active region. In the cutoff region, cutoff means off. So here you have the gate to source voltage which is less than the threshold voltage. There will be no drain current flowing, and the MOSFET will be acting as a switch which is in the off state. In the ohmic or the linear region, the drain to source voltage is less than the difference of gate to source voltage and the threshold voltage. It acts like a voltage control resistor, and this is used for switching which is in the on state. So usually we will be operating our MOSFET in the linear region which is basically the on state. In the saturation or the active region, the drain to source voltage will be greater than the difference between the gate to source voltage and the threshold voltage. This will be acting like a current source, and this is used for amplification purpose. So you have two important purpose. One is the switching and second is the amplification. When you require amplification, you go with the saturation mode or region of operation. When you require the switching mode, you basically go with the linear region. So if the MOSFET is to be off, then it is in the cutoff region. The MOSFET operation is basically shown by this figure where you have the N-channel MOSFET which is in the enhancement mode. So here we are connecting a source between the gate to source, and between the drain to source there will be a current which will be start flowing when the MOSFET will be in the linear region of operation. So this is the equivalent circuit of the MOSFET during the turn on state. So there are different time intervals that we can split from T0 to T1, then from T1 to T2, what is happening between T2 to T3 and T3 to T4. So the gate current will be going and to the load which is connected between the drain and the earth. So the different time intervals that you have, which is the splitting time intervals, you can see through this pictorial representation how the current is splitting up and in which region the MOSFET is conducting and which region the MOSFET is off. So you can see that there are different capacitors which are forming from gate to drain and gate to source, and the current will be flowing when the transistor is in the MOSFET is in on state. The transfer characteristic, which is basically the drain current versus the gate to source voltage, and the key parameters that are involved is the threshold voltage which is 2 to 4 volt typically, and the transconductance which is the change in the drain current with respect to the change in the gate to source voltage, and it obeys the square law relationship in the saturation mode. So you have the drain current which is equal to K times, K means the transconductance parameter, and the difference of the voltage, that is gate to source voltage, and the threshold voltage square. So this is the static characteristic. On the y-axis we have the drain current, and x-axis we have the gate to source voltage. So this is the threshold limit. So before threshold there is no conduction, and after the threshold the conduction will start. So when we divide the region of operation, we have the ohmic region, the active region, and the saturation region, which are basically the cutoff and the switch being the on state and the amplification region. So on state parameters, if we discuss, then is basically the on state resistance which is RDS on. So this is the drain to source resistance when the MOSFET is fully on. So when the MOSFET is basically fully on, then what is the resistance which is between the drain to source? This is known as RDS. This is the most important parameter for any device selection because it determines the conduction losses. Conduction losses is given by the formula which is equal to ID square, which is the drain current square, multiplied with the resistance of the drain to source under the on state. This is specified at a particular gate to source voltage which is typically at 10 volt, and temperature which is at room temperature we take as 25 degree centigrade. The gate drive voltage guidelines says that the gate to source voltage has to be 10 volt, and usually it is sufficient for most application. gate to source voltage 15 volt, it is recommended for the minimum RDS. And when the gate to source voltage is maximum in and around plus minus 20 volt, then this is the absolute maximum, generally the oxide breakdown limit. So this is the guidelines given for the gate to source voltage, how much we have to keep it. Temperature effect also plays important role. So RDS, which is the resistance of drain to source, this will increase with respect to the temperature in and around 0.6% per degree increase in the temperature. And the threshold voltage will be decreasing with respect to temperature, approximately minus 2 millivolt per degree centigrade. Positive temperature coefficient help in the paralleling operation of the MOSFET. We will be discussing a little bit later. Now let us discuss the breakdown characteristic. So the voltage rating, which is because of the drain source breakdown. So breakdown voltage in the drain to source, this is maximum VDS when the device is under the off state. In this case, the range will be around 50 volt to several kilovolt, and we have to choose 2 to 3 times the operating voltage. Here the avalanche breakdown will be taking place in the drain region. Now, if we talk about the breakdown for the gate source, this is the maximum VGS without having the oxide to damage. Typically, this has to be in the limit, which is 20 volt to 30 volt in plus minus region. And this is very critical because the permanent damage can take place if it exceeds this limit. So we need to have very thin oxide layer, about 100 nanometer. Safe operating area. What is that? It basically defines the safe current voltage operating limit. So when the MOSFET is in operation, we have to operate it safely, and as a result, the current voltage relationship should be in the operating limit, and this is limited by the current, voltage, power, and the thermal constraint. When we talk about the thermal, it is basically the temperature. So the advantage is that there is no secondary breakdown in the power MOSFET, unlike the BJTs, where you have the secondary breakdown. Now you may have seen the capacitances, which are known as the parasitic capacitances forming in the MOSFET. So what are those capacitances? One is the main capacitance, which is the gate to source capacitance. This is gate source capacitance, GS. So here you can see gate to source. This is the gate and this is the source. You can have the capacitance forming between gate to drain. So this is the drain and this is the capacitance, which is due to the Miller's effect. The drain to source capacitance, there is connected between drain to source. So three important capacitance are the parasitic capacitance. In the data set, you will be getting the other capacitance, which is depending upon the input, output, and the reverse transfer, which is when we calculate the input capacitance, it is basically the sum of gate to source and gate to drain. Output capacitance is the summation of drain to source and gate to drain, and the reverse transfer characteristic or the capacitance is equal to the gate to drain capacitance. The impact of these capacitances are very important because it determines the switching speed of the MOSFET. Like the gate to drain capacitance will create the Miller effect, and all are voltage dependent because MOSFET itself is a voltage dependent application or a device. Now the body diode characteristic, you have the body diode properties, which is inherent PN junction, which is forming between the drain and the source, and this is always present in the power MOSFET. Here you have the forward voltage drop, which is around 0.7 to 1.2 volt, which is similar to the regular diodes, and there is a reverse recovery time, which is typically slow in the range of 100 nanosecond to 1 microsecond. So these are the properties of the body diode. Some of the advantage, it provides freewheeling path for the inductive load. So when you have the inductive load, you will be having a current in the off state, which the freewheeling path will be providing. So it eliminates the need for external diode, which is the freewheeling diode in case of other applications, so that we don't need it in many circuits. It enables the bidirectional current flow. So you have the bidirectional current flow because of this body diode, and it is useful in the bridge circuit and the motor drives. There are certain disadvantages also. There will be slow reverse recovery and cause the losses. Higher forward drop will be compared to the dedicated diodes, and it may require external fast diode in high frequency applications. So When we require very fast diode applications, then it may be slow in that category and it may be a disadvantage for such applications. So now we will discuss the switching behavior. So why we need to study the switching? Switching is basically in power MOSFET used primarily as a switches. So we are using the power MOSFET as switches. So switching behavior study is very important because we need to determine the switching losses which are significant at a very high frequencies. Switching speed determines the maximum operating frequency, which is critical for the gate-derived circuit design as well. MOSFET switching advantage when we talk about, so these switching advantage are majority of the carrier devices will have no stored charges since they have no storage time unlike the BJTs. Moreover, they have fast switching which are limited only by the capacitances. They are voltage controlled, so no continuous gate current will be there. So these are the advantages of MOSFET switching. There are certain limitations as well, like the parasitic capacitances which are must be charged or discharged. The Miller effect will be there during the transitions. Gate drive capability requirement will also be needed. Switching time definitions like the on time, which is the turn on delay time given by TD on. TR is basically the current rise time from 10% to 90%. The on time is given as the summation of the turn on delay time plus the current rise time, which is the turn on total time. The turn off time is basically given as the summation of TD off, which is the turn off delay time, plus TF, which is the current hold time from 90% to 10%. So this is the total T off time. The switching waveform is given here where the gate drive signal is shown and the gate source voltage which is given at different time instant from T0, T1, T2 to T8 time. These time instants are divided because the waveform of the gate to source voltage have different magnitude from the different time instants. So as we can say that from T0 to T1, the gate to source voltage is increasing linearly. Again, it will increase from T1 to T2, then T2 to T3 and so on. It will be stabilized here from T4 to T5 and then it will fall gradually. The current in the drain, if you can see it, up to T1 there will be no current. Then the current will increase and become stable. After that the current will fall. The drain to source voltage which is falling and then become constant and then increase and then become stable. So there are certain factors which affect the switching speed. The first factor is gate drive current capability. The parasitic capacitances, especially the CGD, which is the gate to drain capacitance, the gate resistance and the load characteristic. These are certain factors which will be affecting the switching speed of the MOSFET. We were discussing about the Miller effect. So let us see what is Miller effect. Miller effect is basically caused by the gate to drain capacitance. This create a plateau as we have seen the switching waveform in the gate voltage during the switching characteristic. It slows down the switching transitions. The total duration of the Miller time can be estimated as the capacitance of gate to drain multiplied with the change in the drain to source voltage by the gate current. The gate charge is basically the total charge which is needed to turn on the MOSFET. It is more practical parameter than basically the capacitances. It is independent of the gate drive voltage and the charge of the gate is basically the summation of gate to source plus the gate to drain charge. Switching time with constant current drive can be obtained as the ratio of the charge of the gate by the current of the gate. That is the total switching time. Gate drive circuit is the requirement, and why we need proper gate drive circuit, which is basically critical because the MOSFET performance depends on the gate drive quality. If you have the poor gate drive, then you will be having the slow switching and high losses will be taking place. Must provide sufficient voltage and the current for the gate to operate. There is certain key requirement for this. The voltage, which is should be 10 to 15 volt for the full enhancement. The current capability to charge the gate capacitance quickly. There has to be low impedance to minimize the gate resistance. Has to be the fast rise or fall time for high frequency operation. The isolation has to be there for high side switches, and the protection has to be there for against the gate over voltage. Gate resistance guidelines, if we see, then it should have the lower RG value, that is the resistance of the gate, so that faster switching can take place and higher peak current even with more EMI, that is electromagnetic interference. Higher RG if you have, then it will be having the slower switching, which will reduce the EMI and prevent oscillation. Typical range that falls for the gate resistance is in the range of 10 to 100 ohms. The gate drive circuit types, if we see, it is a direct drive circuit, bipolar transition drivers, dedicated gate driver ICs, or transformer coupled drivers. If you see the direct drive, these are from the logic gates or the microcontrollers. It is used only for the small MOSFET with low gate charge, and it is limited by the current capability. The BJT drivers are basically the push-pull configuration, which is the summation of NPN and PNP transistors. They are higher current capability and have discrete component approach. The dedicated gate driver ICs are optimized for MOSFET driving. The features include the dead time, shoot-through protections like UVLO, and examples of the MOSFETs with dedicated gate drive ICs are the numbers like IR2110, TC4427 or MCP1416. These are commercial available gate drive ICs. Transformer coupled drivers are provide for galvanic isolation. They are good for high voltage applications, but they are more complex circuit. So gate drive circuits, which are the requirement, can have any of these 4 categories depending upon the requirement. We will be calculating the power losses because of conduction, which is given by the product of the drain current RMS square multiplied with the drain to source resistance under on condition into D, where D is basically the duty cycle. Switching losses are calculated during the on time, off time, and the power during the switching can be calculated as the summation of these on and off voltage multiplied with the frequency of the switching. So we can calculate this E on and E off from the voltage, current, rise time, and the drain to voltage time duration. Gate drive losses can be calculated as the product of the charge of the gate multiplied with the voltage of the drive and the frequency of the switching. Body diode conduction losses we can calculate for the power diode as the product of the forward voltage multiplied with the average current plus the product of RD into IRMS square. So these formulas can be used to calculate the power losses in the MOSFET under different losses conditions, whether it is conduction, switching, or gate drive or body diode conduction losses. Thermal management is also important. So we have the thermal resistance model and heat sink design. Thermal resistance model, we have the formula TJ, which is the junction temperature, is equal to TA, which is the ambient temperature, plus the product of the total power into theta JA. So this is the junction of the ambient temperature. Now this heat sink design, which is the temperature theta as SA, which is sink to ambient thermal resistance, can be calculated using this formula, which is TG max minus TA. All formulas are given here with theta JC, which is basically junction to case thermal resistance, and theta CS, which is basically case to sink thermal resistance. Some of the thermal management tips are: use adequate heat sink area, apply thermal interface material properly, consider forced air cooling for high power, and derate current at high temperatures. So we need to properly monitor and control the thermal effect on the power MOSFET as they are high voltage and high current device. Paralleling of power MOSFETs. So why paralleling is required? Because we need to increase the current capability, reduce the on resistance, should have better thermal distribution, cost-effective solution, and enhanced reliability. So these are the major requirement that can provide us the advantage for the paralleling of the MOSFET. So here we can see that there is one MOSFET and the second MOSFET is there, which are connected in parallel operation with the register of the gate. So this has certain advantage over BJTs, like positive temperature coefficient you will get, self-balancing current sharing, no current sharing registers is needed, and no thermal runaway. Current sharing mechanism due to the parallel operation will have device carrying more current will heat up, higher temperature will result in higher resistance of the drain to source in the on state, higher resistance will result in current reducing automatically, and natural negative feedback mechanism will come into play. So paralleling of MOSFET we need when we need more current. This is the comparison of the power MOSFET with power BJT for different parameters, whether it is control method. So control method, we know that MOSFETs are voltage control device, whereas BJT is current control device. Input resistance is very high for the MOSFET in the mega ohm range. Power BJTs is medium, that is kilo ohms. Drive power is very low in MOSFET, where it is high in BJTs. Switching speed is fast in MOSFET, where it is slower in BJTs. On-state voltage drop is higher in MOSFET and lower in BJT. Secondary breakdown is not applicable in MOSFET, but it is possible in BJT. Thermal runaway, there is no thermal runaway for MOSFET. Yes, we have thermal runaway for BJT. Paralleling operation is easy in case of MOSFET, but it is difficult in BJT. Temperature coefficient is positive for MOSFET but negative for BJT. Frequency capability will be higher in MOSFET and lower in BJT. Cost per ampere is higher for MOSFET and lower for BJT. So this will determine the costing of the device. Voltage capability is limited up to 1000 volt for MOSFET, but power BJT can have higher than 1000 volt. MOSFET selection criteria depends upon the voltage rating, current rating, ohms resistance, and switching parameters. So voltage rating from drain to source, you can choose 2 to 3 times the maximum operating voltage. It can account for voltage spikes on the transient. So consider derating with temperature. If you have the current rating, then it is based on the RMS current when you have the resistive load. Consider the peak current capability and account for thermal limitation. On resistance, generally for the lower resistance will have lower conduction losses. So specified when the gate to source voltage at 10 volt under the temperature of 25 degrees centigrade. So consider temperature rise effect as well. Switching parameters, you have to consider the gate charge because it will account for the switching losses. Gate capacitances will result in drive circuit design, and rise fall time will be for frequency capability. So MOSFET selection criteria under these conditions has to be considered. Some of the major application of power MOSFET is in switch mode power supplies, motor drives, automotive electronics, and other applications like LEDs, battery management systems, solar inverters, and audio amplifiers. Switch mode power supplies, it operate in the buck mode, boost mode, and buck mode converters. It is used in the forward and flyback converters, resonant converters. Motor drive you can have in the 3-phase inverters, servo drivers, stepper motor drivers. In electronics, you can think of using the MOSFET in electronic injection systems, fuel injections control, and electric power steering. So there are wide applications of power MOSFET from industries to automotive electronics as well as the different power electronic applications. MOSFET need protection. So protection can be for overcurrent, overvoltage, gate overvoltage, for temperature, that is thermal, and dV by dt protection has to be there. So we have to take all this into account for the protection. So protection method include use of the snubber circuit, the gate clamping, current sensing, and thermal shutdown. So snubber circuit we will be discussing in detail in the one of the lecture we have discussed, and these are basically the networks comprising the RC network, which are special the circuit for the protection of dV by dt. Layout consideration, we have to be minimizing the parasitic inductances, keep the gate drive traces short, and use ground plane effectively. So whenever we need to use the MOSFET, we need to have proper protection as well as the layout consideration. Practical design consideration, we need to take care of the gate drive design, PCB layout guidelines, and common design pitfalls due to the different conditions which can be due to the gate drive, thermal design, ignoring the parasitic inductances, and insufficient protection circuitry. So these discussions, whatever we do here in MOSFET, generally for the practical purposes, will require the proper caring of the gate drive circuit as well as the layout design, and certain important design pitfalls can take place. Now, there are certain advanced MOSFET technologies which are researched upon, like the silicon carbide MOSFETs, which are having high voltage capability greater than 1200 volt. They have lower on resistance and high temperature operation. There are faster switching speed and higher cost for improving efficiency. So compared to the normal MOSFET or MOSFET, we can have the silicon carbide MOSFET, which will give these advantages. You can have gallium nitride HEMTs, which are basically the ultra fast switching if you need in the sub nanosecond, or very low gate charge, high frequency capability in the megahertz range, or no body diode, which are the advantage for the gallium nitride power MOSFETs basically. You can have super junction MOSFET as well, which are overcoming the silicon limit in terms of the drain to source resistance versus voltage rating. It has the figure of merit, and complex manufacturing process is there for this. These are basically the advanced MOSFET technologies. So the summary of the key takeaways that we have discussed is power MOSFETs are basically the voltage controlled and the majority carrier devices. They are excellent for switching applications due to fast switching. Three main operations we have discussed, that is the cutoff, ohmic, and saturation. On resistance is the most critical parameter for power applications. Proper gate drive is essential for optimal performance, and natural current sharing make paralleling straightforward. So these are basically the key takeaways of the discussion of power MOSFETs. So advantage, we have also seen that it has high input impedance and low drive power. Fast switching is there and no storage time. Positive temperature coefficient, no thermal runaway, easy to parallel and robust operation. So application is dominant from low to medium voltage in power electronics, especially where you required high switching frequency. So in future trends, we have seen that silicon carbide and gallium nitride, which are basically the wideband semiconductors, are gaining the market share. These are integrated with smart gate drivers. We have advanced packaging for better thermal performance, and higher voltage silicon MOSFETs with super junction technologies are the new evaluation. Applications can be electric vehicle, renewable energy, data center power supplies, and wireless power transfer applications. So the future belongs now to the wideband semiconductors, but again we say that silicon MOSFETs will remain important for cost sensitive applications. So this complete our discussion on power MOSFET, which are the workhouses of the modern power electronics. So these workhouses, as they are basically the driving force or the major applications of any power electronic devices. So next lecture we will see on IGBTs, their characteristic, their applications, their types, and so on and so forth. Thank you for now.